We all have a way we see the universe thanks to what research tells us. But now Hubble has just confirmed that something isn't right with our physics. We have been seeing it the wrong way all this time, and in this video you will find out about all that isn't right about our physics. The Genesis. Without the study of the universe, we won't know if the universe is coming, going, or standing still. This is why astronomers have played a good part in finding out about the universe. However, in 1929, American astronomer Edwin Hubble made a shocking discovery after the Big Bang event. The Big Bang event is a physical theory that describes how the universe expanded from an initial state of high density and temperature. After the Big Bang event, scientists believed that the universe would continue to expand more slowly. But according to Edwin Hubble, while observing distant galaxies, he discovered that galaxies' recessional velocity is proportional to their distance. This means our universe was expanding, and galaxies were moving further away from the Earth, retreating faster the more distant they were. Although scientists expected that this expansion would slow down over time, this expansion is accelerating instead. That has put astronomers on their toes. They all want to know what is causing the expansion. The Hubble's constant. There's a need to know the actual size of the universe, hence the need for Hubble's constant. The Hubble's constant has a unit of kilometers per second per megaparsec. There is a direct relationship between a galaxy's recessional velocity and the distance to the particular galaxy. The recessional velocity is measured in kilometers per second, while the distance between the Earth and the galaxy is measured in megaparsecs, which is why Hubble's constant has units of kilometers per second per megaparsec. Let's assume we have a Hubble's constant of 50 kilometers per second per megaparsec, which means for every megaparsecs of its distance, a galaxy will acquire an extra recessional velocity of 50 kilometers per second. The Hubble's constant is represented by HO, and it is a significant number in cosmology because it's the way to have a better understanding of the universe, especially its size. The Hubble's constant sounds very easy to understand, but it's still very difficult to obtain its precise value because to calculate it, we need the recessional velocity of a galaxy and the galaxy's distance from Earth. The recessional velocity is measured by observing the wavelength shifts of spectral lines emitted by the object called object cosmological redshift. Simple, yes? The only difficult parameter is the distance. And one of the ways to measure the distance is by observing the Cepheid variables that live in it. Cepheids travel through a complete cycle from maximum brightness to a minimum, and then the process gets repeated. There's a need to know that a Cepheid's variability period is directly related to its luminosity, which means the longer the variability period, the more the Cepheid gets luminous. The Cepheid is what Hubble used in the first place to measure the distance by measuring the difference between the observed and actual brightness. That way, astronomers were able to estimate their distance using the distance modulus equation. But before they can make the calculations, the relationship between the variability period and the luminosity must be calibrated with Cepheid variables that are close, whose distance can be easily measured using the parallax method. That is when things get a bit difficult. Pinning down the numbers requires accurate measurements of astronomical distances. All of these steps to measure the cosmic distance are called the cosmic distance ladder. This method is a very good one that is supposed to be effective, but with each step the complexities become greater. However, Hubble was able to derive the variation between the velocity and the distance for Hubble's constant of 500 kilometers per second per megaparsec. But the Cepheids can only be used to measure distances from about 1 kilo per second to 50 mega per second. This simply means that astronomers can't fix a constant value just by observing the behavior of galaxies up to 50 megaparsecs. If we really want to know Hubble's constant, we need to turn to exploding stars called the Type 1a supernovae, which is a type of supernova that occurs in a binary system in which one of the stars is a white dwarf. When the white dwarf undergoes a fusion and eventually explodes, the explosions are so bright, making them perfect to calculate longer distances. To achieve that, a project called the Hubble SHOES program was launched. The program stands for supernova HO for the equation of state of dark energy. The discovery. During Hubble's time, he took astronomical images by shining light through a telescope onto a photographic plate and calculated the distance from those images. However, those images were difficult and imprecise. Back when the Hubble Space Telescope was launched in 1990, the universe's expansion rate was so uncertain that its age might only be 8 billion years or as great as 20 billion years. However, after 30 years of meticulous work using the Hubble Space Telescope's extraordinary observing power, numerous teams of astronomers have narrowed the expansion rate to a precision of just over 1%. This can be used to predict that the universe will double in size in 10 billion years. The SHOES team measured 42 of these supernova mileposts, more than double the previous sample of cosmic distance markers. However, when they started gathering information about the universe's expansion, a discrepancy emerged. The SHOES team reported a rate of roughly 73 kilometers per megaparsec, but when taking into account observations of the deep universe, this slows down to about 67.5 kilometers per megaparsec. A megaparsec is a measurement of distance equal to 1 million parsecs or 3.26 million light-years. The team considers galaxies that lie within 2 billion light-years away, which means it measures the present expansion rate of the universe. This suggests that the universe's evolution and expansion are more complicated than we had realized, and there is more to learn about how the universe is changing. Cosmological crisis. For years, experts have been studying the universe's expansion rate since the 1920s using measurements by astronomers Edwin Hubble and Georges Lemaitre. Even after NASA birthed a large space telescope in the 70s, they spent much money and effort on the telescope just to be able to solve the Cepheids problem. Cepheids have long been the gold standard of cosmic mile markers since their utility was discovered by astronomer Henrietta Swan Leavitt in 1912. But as said earlier, they cannot be used to calculate much greater distances. Back in 2019, after the SHOES team reported a value of the Hubble's constant, they had to make sure the value was correct, and to do that, they needed to go back in time. That is because if the expansion rate of the universe can be measured just after the Big Bang, that value can be used to make estimates of Hubble's constant for the present-day scenario. After the astronomers did that, they saw a crisis in front of them. What we know is that after the Big Bang, the superheating of all the matter in the universe released a great amount of energy, and as the universe expanded, the radiation got more redshifted. Through the use of the cosmic wave background, also called the CMB, astronomers were able to estimate how much the radiation redshifted. Different methods were also used to model the expansion of the universe, and when nothing was added up, it became a big crisis in cosmology. The new value. The Hubble's constant is critical to estimating the age of the universe and provides a basic test of our understanding of the universe. It can be used to predict how fast an astronomical object at a known distance is moving away from Earth. Astronomers have tried different methods to achieve greater accuracy in their observational values, and recently they have reached a new milestone. The SHOES team reviewed all of Hubble's data using over 1,000 Hubble orbits and analyzed 42 supernovae milepost data that explode at a rate of about 1 in a year. Finally, they were able to get to a point of 73 kilometers per second per megaparsec, which is again higher than the theoretical prediction of 67.5. That measurement is about 8 times more precise than Hubble's expected capability, but this sample size is larger than any sample size that has ever been used, so we can say there's a 1 in a million chance that the new estimate is wrong. This new result will give room for more understanding of the universe, even though the cause of the initial discrepancy is unknown. And talking about the cause of the discrepancy, scientists suspect dark energy in the universe. Dark energy. This is a phrase the physicists have used to describe a mysterious thing that is causing unusual happenings in the universe. This is the most acceptable premise to account for the accelerated expansion of the universe. As of 2021, there are active areas of cosmology research to understand the fundamental nature of dark energy. Assuming that the CDM model of cosmology is correct, as of 2013, the best current measurements indicate that dark energy contributes 68% of the total energy in the present-day observable universe. The mass energy of dark matter and ordinary matter contributes 26% and 5% respectively, and other components such as neutrinos and photons contribute a very small amount. The simplest explanation for dark energy is that it's an intrinsic fundamental energy of space. Since energy and mass are related according to Einstein's equations, Einstein's theory of general relativity predicts that this energy will have a gravitational effect. It's sometimes called vacuum energy because it's the energy density of space. The big vacuum, repulsion, and attraction. The big question scientists asked was what causes the motion of the universe at that speed and in that direction. Until now, scientists assumed that a dense region of the universe is pulling us toward it in the same way gravity made Newton's apple fall to Earth. According to research, scientists believe that our galaxy is not only being pulled but also pushed. Therefore, this is a case of both attraction and repulsion. Researchers have discovered a very large region in our extragalactic neighborhood sparsely populated by galaxies. This void exerts a repelling force on our local group of galaxies. Scientists at first assumed that a dense region of the universe was pulling us toward it, the main reason being something they described as the Great Attractor, a region of a half-dozen rich clusters of galaxies 150 million light-years from the Milky Way. Soon after that, attention was drawn to an area of more than 24 rich clusters called the Shapley concentration, which sits 600 million light-years beyond the Great Attractor. Both of these attractors were pulling the galaxies toward them. By 3D mapping the flow of galaxies through space, it was discovered our Milky Way galaxy is speeding away from a large, previously unidentified region of low density. Because it repels rather than attracts, this region is called the dipole repeller. In addition to being pulled toward the known Shapley concentration, we now know there is also a push away from the newly discovered dipole repeller. Thus, it has become apparent that there is repulsion and attraction in our location. The presence of such a low-density region has been suggested previously, but confirming the scarcity of galaxies by observation has proved challenging. Using powerful telescopes, among them the Hubble Space Telescope, they constructed a three-dimensional map of the galaxy flow field. Flows are direct responses to the distribution of matter away from regions that are relatively empty and toward regions of mass concentration. By identifying the dipole repeller, the researchers were able to reconcile both the direction of the Milky Way's motion and its magnitude. They expect that future ultra-sensitive surveys at optical, near-infrared, and radio wavelengths will directly identify the few galaxies that they believe lie in this void, which would directly confirm the void associated with the dipole repeller. The big vacuum. As we know, the Earth revolves around the Sun. The Sun does not embody a rigid structure either. The Sun races around the center of the Milky Way at a speed of 137 miles per second. But even here, the cosmic merry-go-round is far from coming to a standstill, together with the Andromeda Galaxy and about 70 dwarf galaxies. Our Milky Way is part of a local group that comprises objects within a radius of 5.8 million light-years. Researchers assume that the individual components of the local group are gravitationally bound to each other with a share of 95%. The largest part of their visible mass is in our Milky Way and the Andromeda Galaxy. However, the individual group of members are not evenly distributed but form individual subgroups depending on their gravitational binding. This void is so large that it can accommodate up to 500 dwarf galaxies. However, we've only known about 70 galaxies in this group. Some scientists believe that those galaxies are unknown because of dark matter. The exact size of this space is not known yet, but according to estimates, the void has an expanse of 150 and 230 million light-years. The corresponding area can be divided into 3 different sectors. The individual regions are separated from each other by filaments, and these connections are composed of visible and dark matter that lies between large galaxy clusters and superclusters on the largest known scales. The cosmos appears as a kind of galactic web formed by these same filaments. The areas enclosed by this honeycomb structure are in turn called voids. However, these voids contain a few galaxies' positions and influence gravity, causing a distribution pattern in the universe. It causes matter to clump together in colloquial terms as a result of mass attraction. Galaxies thus come together in the form of clusters and chains between these cosmic accumulations in areas in which we have only a few or no galaxies at all. Before this discovery, the researchers found out that the Milky Way is part of a large flat galaxy cluster. The local sheet also embodies the boundary region to the ominous local void. The current discovery is that the Earth is located about 23 megaparsecs from the center of the local void. With NASA's James Webb Space Telescope coming into full swing, we can expect to have sharper resolutions and more knowledge about the universe in the future. According to reports, Webb is far more sensitive to electromagnetic waves than the Hubble telescope. The instrument works from the red part of visible light to the mid-infrared spectrum, and because of how powerful it is, we expect more details about the universe soon.